Hey everybody, welcome back to chemistry, and we're continuing on through chapter 3. And now we're getting into a place which is pretty important, in that what we're going to have to do is take formulas for compounds and convert them to names, and then do the vice versa. We're going to have to take names of compounds and then convert them back to formulas. And so before we get into the details of that, there are a couple of things that you need to know. So one thing you need to know is you're going to have to be able to look at a name or a formula for a compound and figure out what type of compound it is, whether it's a molecular compound, an ionic compound, or an acid. And the reason you have to do that is because these different types of compounds have different rules to find names for them or define formulas for them. So we have to go over that. And then another thing that we want to go over before we start doing the naming and the writing formulas is I want to talk about something called monatomic ions and then teach you how to figure out what charges monatomic ions have. So one thing I want to sort of remind you of is that there's really a big difference between molecular compounds and ionic compounds, and this is in part the reason why they have completely different rules for naming them. So you can sort of look at that slide there. There I have an example of a molecular compound, which is propane. So the molecule propane, each molecule has 3 carbon atoms bound to 8 hydrogen atoms in a particular configuration. And so you can sort of see those individual propane molecules there in that picture. So the bonds between the atoms in the propane molecule are covalent bonds. Now, this is again an example of a molecular compound, and so it's going to have its distinct rules to find a formula for that compound or to create a name for the compound. Now let's compare that to another type of compound. So this is ionic compounds. So while molecular compounds were made of atoms, ionic compounds are not so much made of atoms, they're more made of ions. And so the ions are all bound together there, positive and negative ions, and they're all held together by ionic bonds. And so these really are different kinds of compounds, and so they have different rules to name them, and so you'll have to learn those eventually. And then there's sort of a subset of molecular compounds that you have to be able to identify, and these are the acids. And the reason is acids have their own rules to name them. Okay, so the first thing I need to go over is you need to learn how to figure out whether a compound is either ionic, molecular, or an acid. And so let me show you how to do this. So the basic idea is this. You have a molecular compound if you find that all the elements in the compound name or formula are all nonmetals. You have an ionic compound if you find that the elements in the compound are mixtures of metals and nonmetals. And finally, you have an acid if you are looking at a formula and the first letter is H, or you're looking at a name for the acid and the word acid appears in the name. Okay, so here I've sort of drawn out a flow chart on how to figure out if you have a name for a compound, whether you're going to use the acid rules for figuring out the formula, the molecular compound rules for figuring out the formula, or the ionic compound rules for figuring out a formula. So what you have to first do is just look at the name of the compound. And the first thing you need to do is check if the word acid is in that name. And if the word acid is in that name, then what you do is you write a formula using the rules for figuring out the formula for an acid. Now, let's say you're looking at the name again and you don't see the word acid. Then you ask yourself a second question. The second question is this. This name, does it have a metal in it? And so if the name has a metal in it, then what you do is you recognize that this is probably a compound which has a mixture of metals and nonmetals, and therefore it's an ionic compound. And so you need to know the rules for writing out formulas for ionic compounds. Now, let's say you're looking at the name and none of those elements there are metals, they're all nonmetals. If that is the case, then what you have is a molecular compound. And so to write out a formula for a molecular compound, you use the rules that teach you how to do that. Now, another thing that will happen is that maybe instead of taking a name to a formula, you will have to take a formula for a compound and bring it back to a name. So you, again, looking at the formula, have to identify whether the formula is that of an ionic compound, a molecular compound, or an acid. So how do you do that? So when you're looking at the formula, the first question you ask yourself is this: is the first letter of the formula an H? And if it is, then that formula is an acid. And so you'll have to use particular rules to figure out the name of the acid. Now, if you don't see an H as the first element of that formula, then you ask yourself this question: does the formula contain an element that is a metal? And if it does, then you probably have a formula which is a mixture of metals and nonmetals, and that will be an ionic compound. And so you'll have to use the rules for taking a formula for an ionic compound and figuring out its name. On the other hand, if you're looking at the formula and all elements are nonmetals, there's no metal element in the formula, then you have a molecular compound, and you'll have to use rules for molecular compounds on how to figure out the name. Okay, so what I want to do now is just sort of go through some examples of how you do this. What we're going to do is, for those 9 compounds I've listed on the left, all we're going to do is figure out whether these compounds are ionic compounds, molecular compounds, or they're acids. And then later on, we'll talk about how you would go about figuring out what the formula or the name is. Okay, so importantly, what you have to do is you need to have your periodic table out. And so you have to separate the periodic table into metals and nonmetals. So first off, let me draw the staircase line that separates metals from nonmetals. And so you go over to boron here, you go to the left of that, and you draw a staircase line so that the right side of the line includes boron. So I'm hoping you can get used to doing this. And you'll know that to the right side of the staircase line, you have nonmetals. Now, on the left side of the staircase line, you have metals, except for hydrogen here. So let me circle this. This is very important. So with the naming rules, you should just remember that hydrogen is always a nonmetal. Okay, so once you know that, you are ready to figure out whether the names or formulas I have listed are they ionic, molecular compounds, or acids. So let's look at the first name, it's sodium chloride. So what is the first question you ask? The first question you ask when you're looking at a name is, does that name have the word acid in it? And you can see the answer is no. So sodium chloride is not an acid. So you go to the next question. The next question is, in that name, do you see an element that is a metal? So you have to check that. So we have sodium and chloride. So you have sodium here is a metal, and then we have chlorine over here, which is a nonmetal. So we have a name here with sodium, which is a metal, and then chloride, which is a nonmetal. So you have a metal and a nonmetal bound together. You have an ionic compound, and in the future, we'll teach you how to take that name and figure out using distinct rules that the formula truly is NaCl. Okay, let's go to the next one. So we have a formula now, it's HF. So the first question you ask yourself when you see your formula is this: does that formula have a first letter that is an H? If it does, it's an acid. If it doesn't, it's either a molecular or ionic compound. And so what you can see in that formula, there is that first element, which is an H. So this is an acid. And so later on, you will figure out how to take that acid formula and figure out a name for it. Okay, next compound is nitrogen dioxide. Again, you have a name, so ask yourself this first question. In that name, do I see the word acid? And the answer is no. So nitrogen dioxide is not an acid. And so the next question you ask is this name have a metal? And so we need to check nitrogen and oxide here. So here is nitrogen, and oxide is just a suffix change for oxygen, which is here. And what I think you can see is that neither nitrogen or oxygen, which is oxide, neither of them are metals. They're both nonmetals. And so if this is the case, then this is a molecular compound. And you use distinct rules for finding the formula. Okay, so the next compound down, number 4, we have a formula. It's a little bit more complicated. It has parentheses there. So again, when you see a formula, ask yourself this first question. Do I see a H as the first element in the formula? And the answer is no, so it's not an acid. So the next question you ask is there a metal in this formula? And so you can look carefully at these elements. We have copper, chlorine, and oxygen here. And so copper is here, which is a metal, and then chlorine and oxygen are nonmetals. And so we do have a metal here, so this is an ionic compound. Okay, next name. We have nitric acid. So the first question we ask is, in that name, do we see the word acid? And if the answer is yes, this is an acid. So to figure out the formula for this, you would need to know the rules for taking a name of an acid and define a formula, which we'll go over later. Okay, next one. We have CCl4. So again, it's a formula. What's the first question you ask? The first question you ask is there an H or a hydrogen as the first element in that formula? And the answer is no, so that is not an acid. Okay, what's the next question you ask? You ask is whether carbon or chlorine are metals. And if you look carefully, you will see that carbon here and chlorine, neither of them are metals. And so this is a molecular compound. Okay, hydroselenic acid, that is a name. So what's the first question you ask? You ask yourself, do I see the word acid in the name? And you do. And so this is an acid. Okay, the next compound, C2H2. So it is a formula. And so what do you ask? What is the first question you ask for a formula? The first question you ask about a formula is, does it have hydrogen as the first element? Now be careful, it does have hydrogen as an element in the formula, but it's not listed first. Because the hydrogen is not listed first, this is not an acid. It would have to have H listed first to be an acid. So it doesn't have H listed first. So this is really not an acid. So the next question you ask yourself is either the carbon here or the hydrogen are either of those metals. And they're both non-metals. So this is not an ionic compound. This is a molecular compound. Now there is one exception to the rule that if you have an H in front of the formula, it's an acid. And that one exception is water. So by the rules I just told you, you would say, the formula H2O. So we see an H in front, and so that would be an acid. This is the exception, or one exception that I know about, that when you have water with the formula H2O, you do have an H in front, but is not considered an acid. Because it's water, it is considered a molecular compound and not an acid. Okay, so let's move on. So we had recently talked about what polyatomic ions are. And so you might remember that polyatomic ions are where you have a bunch of atoms bound together, and then the whole thing has either a positive or negative charge. Now what I want to do is talk about what monatomic ions are. So again, while polyatomic ions are where you have a bunch of atoms bound together and they have a charge, a monatomic ion is where you have a single atom with a charge. And so there are a number of those that you will have to memorize. And so you'll have to memorize what the ion is and the value of its charge. Now, before we get into that, let me point out that monatomic ions can be broken down into two types. There can be something called monovalent ions, which I'm going to write here, monovalent ions, versus polyvalent ions. So what a monovalent ion is where you have an atom and it can only have one possible charge state. And so all the ones you're looking at in this table here, they're all monovalent ions. Now, a polyvalent ion can have two different charge states. So an example of a polyvalent ion really quick is copper. Because copper in some compounds will have a single positive charge, but in other compounds, it will have a 2+ charge. And so there are two states that copper can assume. And so it really is a polyvalent monatomic ion. Now, how about sodium? Sodium can only be, when it's charged, a positive. That is the only possible charge that it could possibly have. And so for that reason, sodium is a monovalent monatomic ion. So what I have listed up here in the periodic table are the monovalent monatomic ions. And so let's go through them. So when you look at the first column of elements here, these are the alkali metals. And so here we're showing that the alkali metals, all of them can lose an electron. When they lose an electron, they become positively charged. Now note that these alkali metals can never be anything but positively charged. They can never be negatively charged. They cannot be too negative, or they cannot be too positive or three positive. They only can assume a positive charge. So these are monovalent ions that are monatomic. And so it would be good for you to remember, if you can, that here, that on this column here, when these atoms become ionized, they will assume a +1 charge state. Okay, so now let's look at the second column over. These are the alkaline earth elements, and so they can become charged. And so I want you to notice when you have alkaline earth elements and they become charged, they don't lose one electron, they lose 2 electrons. And so they assume a 2+ state. And that's the only possible charge state they can assume, and so those are monovalent ions. Then we'll skip over the transition metals for a moment. And then I want you to notice in group 13, what we have here is aluminum. And aluminum, when it becomes charged, will lose 3 electrons, and so it'll be 3+. And these monovalent ions that all have a positive charge state, they're all metals. So when metals become charged, they lose 1 or 2 or 3 electrons, and they either become +1, +2, or +3. And so as you would expect, these metals are going to be on the left side of the staircase ladder. But look to the right side of the staircase ladder. So the right side are the nonmetals. And what you'll see, the nonmetals do not have a positive charge state. They have a negative charge state, which is kind of what we were talking about before, that nonmetals tend not to want to lose electrons. They want to gain 1, 2, or 3 electrons, and they will have a negative charge state. So let's go to the end of the periodic table. So this last column of elements here are the noble gases. Now, you might remember me talking about the noble gases before, and I said the atoms of a noble gas tend not to want to gain electrons and get a negative charge, nor do they want to lose electrons and become a positive charge. So they really never have any kind of charge state. So just to note that noble gases will never have a charge. So I'm going to put a 0 there over the noble gases. Now, let's look at the next column to the left here. These are the halogens. And what you can see is that the halogens, when the halogens become charged, they will tend to want to gain 1 electron. So they'll get a -1 charge state. The next column over, this includes oxygen, sulfur, selenium, tellurium. When they become charged, they tend to want to gain 2 electrons. And so these are going to be -2. And then we have nitrogen. When it becomes charged, will tend to gain 3 electrons. And so when it does, it becomes a -3 charged. And so again, all the ones you see here that have negative charges, they're all nonmetals. Okay. So what I've done here is I've sort of drawn out an abbreviated periodic table. So let me sort of explain why is it that, say, elements in the first column are +1, and why is it elements in the next to last column are -1. So let's just focus on hydrogen here, and let's take a look at the picture. So here I've drawn, to the best of my ability, a hydrogen atom. So you see a dot there in the middle with a little positive charge. That indicates the nucleus. And then I have sort of a ring around it. And then there's a dot there. So that ring represents an energy level, and the dot represents an electron. Now, for now, what you can think of that ring as maybe an orbit the electron is traveling around in. Now, we now know today that electrons do not travel in orbits around atoms, but for this explanation, that's good enough. Okay, so what I want you to notice is that with hydrogen, I've sort of indicated down there that there's 1 proton, 1 positive charge, and 1 electron, 1 negative charge. And so this is the hydrogen atom element. So at this point in time, the atom is neutral. Now, if you go across to the other end of the periodic table, helium will have 2 protons in its nucleus, and so it has 2 positive charges, and then there are 2 electrons in the first energy level. To note, you'll learn later with the first energy level, once you get 2 electrons in it, it is considered full. And when you have a full energy level, the atom becomes very stable. Now, what do I mean by full? Meaning that it's maybe not so easy to pull off an electron, or it may not be so easy to add an electron. It's just very stable the way it is. So just keep in mind when you have the inner ring, the first energy level with 2 electrons, it is full. Okay, so now we go down to the next element, lithium. So lithium has 3 protons in its nucleus. And so now what you'll notice is that it also has 3 electrons. And so the first 2 electrons go in the first energy level. The next electron goes into the second energy level. And what you can see as you go across the periodic table, you're adding protons to the nuclei. And so the element is changing identity. You're going to 4 protons, which is beryllium, 5 protons, which is boron, and so on. And as you're doing that, here in this example, the atoms are remaining neutral, and so you're adding electrons as well. So with beryllium, atomic number 4, in addition to its 4 protons, it has 4 electrons. Now look where they're going. 2 electrons in the first energy level, which is full, 2 electrons in the second energy level. Now, you can add more electrons to the second energy level. You can add 3 electrons now in boron, 4 electrons in carbon, and so on, until you get all the way out to neon. When you get to neon, then you have a total of 8 electrons in the second energy level. And when you have that condition, then that second energy level is considered to be full. So this is the second energy level. Let me kind of draw that a little bit better. And there are 8 electrons there indicating it's full. And again, when you have a full energy level, then the atom is just super stable. Okay, now if you were to go up another proton, we would be at atomic number 11. So where would the new electron go? Well, it goes out to a further out energy level, which is the third energy level. And again, as you go across the periodic table, you add in electrons to the third energy level. And so the third energy level becomes full when you have 8 electrons in it. Okay, so now we're at sort of a point to understand why is it that elements in the first column tend to want to lose electrons, become positively charged. And it's actually a pretty simple reason. So let's just focus on lithium for a minute. So if you look at the lithium atom, what you'll notice is that there are 2 electrons in the first energy level, so it's full, and then there's 1 electron in the second energy level. So lithium can become more stable if it loses 1 electron in the outermost energy level and it pops off. And if that happens, then lithium is down to 2 electrons. And so then this last energy level basically disappears. It's no longer there. And so lithium now, although it has 3 protons, it has 2 electrons now in the first energy level, and it's stable because it has helium stable configuration. So again, 3 protons, 2 electrons, and it becomes very stable. If there are 3 positive charges and 2 negative charges, the total net charge is 1 positive charge. And so the same thing goes down here. So with sodium, there the electron that could leave is now not in the second energy level, it's in the third energy level. And so when that happens, then the remaining energy levels of sodium are filled. So by losing 1 electron, it becomes very stable, and it's said to have neon's electron configuration. Now, how about the next column over? So here in this case, it's not so much 1 electron these atoms need to lose, it needs to lose 2 electrons, and then it gets that stable noble gas configuration. And for the next elements, boron and aluminum, there are 3 electrons in the highest energy level. So if it loses those 3 electrons, then the lower energy levels are full and the atoms will be stable. And they'll be ions when they lose those electrons. Now, again, let's go back to the end of the periodic table. The noble gases, they all have stable electron configurations. So let's consider fluorine. Right now, there are 2 electrons in the first energy level, and then there are 7 electrons in the second energy level. So a question asked is, how can we easily make fluorine stable? Can we add electrons or take them away? So it might be a little difficult to take away 7 electrons from the second energy level. That's possible though, but an easy way to make it stable is by adding electron to the second energy level. By adding electron to the second energy level, then it has 8 electrons in the second energy level, and it has the stable neon electron configuration. Now, guess where that electron comes from? Well, it could come from lithium. For example, lithium wants to lose an electron to get its stable configuration. Fluorine wants to gain it, and so when it does, it gets its stable configuration. And again, let's look at the charges now. When lithium loses an electron, it will become positively charged. When fluorine gains an electron, it will become negatively charged because now there's one extra electron. And so you have ions there which bind together. So again, the column next to the noble gases should have a -1 charge because they tend to want to pick up 1 electrons. With the next one over, to develop that stability, they want to pick up 2 electrons, so they tend to be -2. The next one will be -3. Carbon can go either way. It can be either -4 or +4. Okay, let's move on. So I want to continue on giving you some additional monovalent ions that you need to know about. And so they're the ones that I have here before, but there are a few others that you need to know about. So this first one here that I just brought up is the ion of scandium. So scandium is here in that when it becomes ionized, it tends to want to lose 3 electrons. So zinc here, when it becomes ionized, tends to want to lose only 2 electrons. Silver only wants to lose 1 electron. And then cadmium only wants to lose 2 electrons. And so again, these are examples of monovalent islands. Now, you will notice there that we have a lot of metals that we have not talked about. And so the reason why we haven't talked about them is that these other metals are not monovalent ions. They are polyvalent ions. And so when you have a metal that is a polyvalent ion, it can assume 2 or more charged states, and which one it assumes depends on the compound it's in. Here is an example of a polyvalent monatomic ion. It's copper. And so what you can see there is copper can either be in the plus state or in the +2 state. And it just sort of depends on what the counter ion it's bound to. Now there's another one that you should know that's iron. Iron can either be in the +2 or the +3 state. And again, what state it's in sort of depends on the compound it's in and the counter ion it's bound to. Now, one thing you should know is that all the other metals in the periodic table, you should assume that they are polyvalent for the test. Now, I and no one else expects you to know, for example, that this element here, which is nickel, can either be +2 or +3. That's a lot to memorize. So you don't have to memorize that, nor do you have to know what the states of these metals are. They're all polyvalent, and so these are all polyvalent as well, and then these are polyvalent, and then these down here are also polyvalent. You don't have to memorize that these monatomic ions are polyvalent, and you don't have to know what their different charge states are. Okay, so now what I want to do is talk a little bit about what you're going to be seeing in the future videos. And so in video number 21, what you're going to be doing is you're going to be taking the name of an ionic compound and converting it to a formula, and that's in section 3.3 in your book. Then in video number 22, you're going to be doing a bunch of things. You're going to be taking an ionic compound and converting it into a name. This is mentioned in section 3.4 in your book. And then next, you'll be taking a name for a molecular compound and figuring out the formula, which is in 3.2 in your book. And then the formula of a molecular compound into a name, which is also in 3.2 in your book. And the final thing we're going to go over is figure out how to take a formula for an acid and converting it into a name, which is in section 3.5 in your book. So thank you for listening to that. We'll see you next time.